But if that's the direction of the current that goes with this one, we're saying this is number 4. It looks to me like there's a wire kind of here with the current going into the board and a wire here with the current coming out of the board. So if I use the right-hand rule, current, current this way, magnetic field this way, that appears to be a force that way on the wire. And then this one coming out of the board, current this way, magnetic field up, so that'd be a force that way on the wire. So I think that produces, force that way and that way on the wire. What's that? It'd be the exact same thing, just in the other direction. So it would flip it the other way. They'll be the same size. So this is already at maximum. If the angle were changed, that would change the size of the force. It'll be the same. Yeah. So you get the same size torque as long as you're oriented this way to the wire. Yeah.
So, do you put the lever on in the middle then? Because it would be spinning like this.
If we assume that there's no gravitational force acting on the loop, or otherwise you'd have to have something to force there to be an axis. Like when we made our motors, we forced there to be an axis by using a wire as our axis and having it be suspended due to the loops in our stand-ups. But if this were being done in space, I wouldn't need that because the only force acting on the loop would be the magnetic force, and therefore this system would rotate about its center of mass, which would be a point probably right, here in the middle. Does that make sense? So the size of those forces, I'm going to use S for side length real quick, but the size of those forces will be IS times B, and it would be times the sine of 90 degrees because we have currently the magnetic field and the current are 90 degrees to each other. Is that good? So then the torque will be the torque arm length, which is S over 2, times this force, ISB sine 90 degrees, times the sine of the angle between the force and the torque arm, which also happens to be 90 degrees right now. Once it starts to move, it won't be anymore. And there are 2 of these, right? 2 torques, 1 from each of those forces. So get rid of the sine to 90s, get rid of the 2's, and we get that the torque is I S squared B. Put everything in terms of meters for this because Tesla is in meters. So the 2 centimeters per side, that'd be 0.02 meters. And the 1.5 amps can stand. So this will be 1.5 amps times 0.02 squared times 0.2 Tesla. And this will leave you with an answer in meter newtons. Whatever that is. I don't know. Small amount of torque. All right. That was question number 4. All right. Yeah. Number 2. All right, question number 2. A group of electrons are moving in the same direction at the same speed. Suddenly, a magnetic field of 5 Tesla is switched on perpendicular to the velocity of the electrons. It is then seen that the electrons oscillate at a frequency of 20 kilohertz. What was the speed of the electrons? All right. Do you know what a hertz is? It's from last semester, or it would be from your first semester of physics, but a hertz is an oscillation per second. So 20 oscillations per second. They're going in a circular path, though. The sudden appearance of the magnetic field means that an electron passing this way, being exposed to a sudden magnetic field, and I'm just picking a random direction that is perpendicular to the motion of the electrons, will suddenly cause the electrons to travel in the circle. And since the magnetic field is everywhere, the direction of their motion, the shape of their path won't be semicircular because they didn't enter a region where there was suddenly a magnetic field there. The magnetic field is everywhere. So all of the electrons start traveling in a circle. But of course, we've got to find the direction of that circle, and you should prove to yourself that the direction of that circle is suddenly this way. Because if I use the right-hand rule, the force on those particles will be downwards because they're electrons. The right-hand rule suggests upwards at the start, but they will start all oscillating by being pressed downwards, and therefore they'll have this clockwise direction of motion based on this set of parameters. We don't have the radius of motion here, but we have other information that we can use here. So we'll have to come back to this, I guess, tomorrow. But all right, so in dealing with the lab itself, you're going to have your compass, and identify what is north so that you have an understanding of where north is, and point the N that is fixed, the N that's printed, leave that facing north. So when you move it to your loop, you want to make sure that wherever the N is on the actual compass, that stays facing north. You're going to have your loop of wire off to the side. You want it aligned with magnetic north when there's no influence of a magnetic field. But once you run current in this wire, you're producing a magnetic field in one of those two directions. It'll be pretty easy to figure it out because the needle's going to be deflected in that direction. So take your compass, bring it into this area, connect the bulb. I can't do it. I can't select what I want. Boy, I can't do anything right. Well, I'm glad you all are here for this. There we go. All right, so you're gonna get something like this. Oh my God. I am about to lose my mind. There. All right, something like that. So you get a deflection. Measure this deflection. It's gonna be in degrees because that's what's already marked on the compass. Whatever the deflection is, have the person with the steadiest hands hold the compass and try to brace yourself so your hands aren't shaking too much. There's not going to be a whole lot you can do. It's going to oscillate, and it's going to oscillate until friction brings it to rest, which could be a little while. But if you're tilting it and turning it, you may drive those oscillations, and that might make it go on for a much longer period of time. Okay? So during that, you want to record, and let's talk about the data chart that we're going to have here. You want to record the deflection angle. And you'll have it in degrees. I don't know that you have to convert it to radians, but when I did this a couple of months ago, I did. Now, set that all aside. And when I say set it all aside, I mean set the parts of the experiment aside that aren't the loop. For the loop, you need to measure its radius and you're going to need to measure the number of loops, which based on my preliminary thing is going to be between 2 and 3 loops. Your magnetic field should be something around there. But we don't have a direct way of measuring the current. So to measure the current, we'll just use Ohm's law. So to do so, the resistance should be constant. Measure it once. So just use a multimeter for that. And then just measure the voltage through the loop. So keep the voltmeter on there and set up a simple circuit that has a couple of light bulbs arranged however you want. The whole goal of the light bulbs is to manipulate the current in the loop. So then your loop and back to your 6 volts. You're putting the voltmeter parallel with the loop. So just take another set of alligator clips and clip your leads right onto that and leave it on the loop the whole time. And this is also how you would measure the resistance, but you can't measure the resistance of the loop while current is passing through the loop. So measure the resistance of the loop separately before you create the circuit. Does that make sense? Now, what you do for a set of light bulbs here is your choice. We're just gonna use the Christmas bulbs. You don't really need to know their resistance because you're measuring just this voltage. And that voltage will depend on whatever their resistance is. So that part's not important. But understand you need to fluctuate the voltage as much as possible, but you don't want to peg the needle. So you can run the bulbs in series or parallel. Obviously, running them in parallel is going to increase how much current you have, and therefore it'll also be increasing the voltage across the loop because it's decreasing the overall resistance here. You saw just from our quick example that we were able to move from about that the 2 bulbs in parallel deflected the needle more than just the 1 bulb in parallel, so you can see a clear difference. But with no bulbs, the deflection is just too great. Now, I am thinking that we could reduce the deflection by reducing the number of loops. So maybe instead of having 3 loops from 1 meter worth of cable, we drop it down to 2 or even 1 loop. There's something wrong with attempting those things. When I did it, we did it with 3 loops and we used 4.5 volts and it worked out okay. But we're trying different things here. So if you want to, instead of trying to play this whole resistor game, you may find that it might work a little bit better if you reduce the number of loops. The problem is that reducing number of loops also reduces the resistance, right? And that's going to increase the current draw from the battery. So there's a bit of a balancing act here, and I don't know what all the variables might be. So there's no harm in trying different things. What we don't want to do is break the meters. So if we can, make sure the 1 line in the common and 1 line in the voltage/resistance. Right? That's the one that will ensure that the meter is protected and shouldn't have any difficulty taking your data. Make sure you turn the dial to measure the appropriate thing. All right? Anyways, what you're gonna have over here probably will be voltage. Now, I think a spreadsheet is probably the best way to analyze this, but let's talk about what we have to do next. The actual analysis is we have a magnetic field in one direction that is an unknown, and a magnetic field in another direction that we are calculating. Right? You're going to run a calculation, and we are seeing a deflection in the compass. Now, we don't know what this unknown magnetic field is. We do know that we'll call this B applied and this B of the earth. Is that okay? We know that the tangent of that angle has to be B applied divided by B of the earth. Make sense? So we can, from the deflection angle, say that B of the earth equals B applied divided by the tangent of the angle. I think we just do a simple plot with multiple applied magnetic fields, multiple angles, and plot it. In fact, if we plotted it this way, with this on the y-axis and this on the x-axis, our slope should be the tangent. Not sure that probably worked. That's not going to work. Let's not do it that way. Let's do it this way. Let's plot the applied on the y-axis and the tangent on the x-axis. And that way our slope will be the magnetic field of the earth. That'll work better. Yeah, let's do that. Because we have the angle. So, actually, you're right. We could probably just leave it on degrees as long as you set your calculator for degrees. If you're going to use Excel to do this, Excel defaults to having their tangent in radians. So you would have to tell it that you're using degrees. So it might just be easier to convert your value to radians if you're going to use Excel for the plot. Now, the National Geologic Survey has a website where you can type in your zip code and it will tell you the strength of the average magnetic field at that point in the earth. I'm going to look that up while you guys are doing the lab so we can make a comparison. When I did this lab, I wasn't even close. Just want you to be aware. I was in the same order of magnitude. But I was not near the number. But it did give order of magnitude, so I felt like I had accomplished something. So just so you know, I won't expect this to be accurate for the actual magnetic field of the earth. There's just too many things that we are doing that are probably error prone. Holding the compass being one of them, and the cheapness of the compass probably being the other. All things outside of our control. What I'm really hoping you will be able to do is see the direct relationship between something that is unseen, which is the current you're trying to put through that loop, and the creation of a magnetic field. The deflection of that needle is truthfully your evidence that you are generating something that is changing the nature of the field in that space. Does that make sense? All right.